you are in the electrochemistry part. I'll explain later, but my name is Chad St. Clair. I'm a professor and materials engineer, and I'm here as a moderator or facilitator for today's talk. I want to start by acknowledging that we're on the unceded ancestral and territorial lands of the Musqueam people. And though we might say, well, there may not be a close connection to fluorescence microscopy, there is a large connection to the intended application areas, I think, that today's speaker is going to talk about in terms of clean energy and the fact that the Musqueam people here have for millennia been stewards of the environment here. So thinking about how we can try to have less impact is quite important, and the work that's been talked about today is definitely going in that direction. So I'm very happy to introduce someone who's still a relatively new colleague of mine in the Department of Materials Engineering, Dr. Kiana Amini, is an assistant professor. She did her bachelor's degree in chemical engineering, which we're not judging you for, in Sharif, and then went on to University of Waterloo, again, and from that part of the world. I'm not going to judge you about your choice of schools, and then went on to Harvard University as a professor of materials science, mechanical engineering, where she did really groundbreaking work and continues to do groundbreaking work. Just a paper published today or yesterday in this area of redox flow batteries. So it's really very nice, and I look forward to learning something. As I said, I know nothing about electrochemistry, although people like Dan for 20 years have been trying to convince me to learn about this stuff. So I'm really looking forward to learning about this intersection between technique and application that Kiana's going to talk to us about today. So please take it away.
Thank you so much for the introduction, and hello everyone. Thanks for attending my presentation today. In today's presentation, I'm going to talk about in situ characterization techniques, but with specific focus on electrochemical systems. And so through the talk, first, I'm going to talk why electrochemical systems matter in the first place, and then why in situ Operando techniques or characterization techniques is critical in this context. And then I want to show the importance of electrochemical systems plus characterization techniques in the context of electrochemical carbon capture systems. And then finally, we conclude with takeaway points. So why electrochemical systems matter? Well, electrochemical systems, just by looking at the applications that they have and they continue to show that they can have, are the engines of the clean energy future. So electrochemical devices, the most famous one we know about, batteries. It has made it possible for us to have portable devices, electric cars, energy storage devices, but also other phenomena can be electrified: carbon capture, water desalination, hydrogen storage, extracting metals, valuable metals, extracting lithium, electrosynthesis. So electrochemical devices matter because they have broad technological impact. And also, because they are voltage driven, so we apply a voltage, we derive a reaction of interest, they don't need to rely on high temperature and high pressure. So in principle, they can be operated in ambient conditions. They are easily integratable with renewable sources. You connect it to solar panels, wind turbines, and you can convert electrical energy to chemical reaction or vice versa. And they are modular and scalable, have modular design. They are scalable. We've seen devices from small scale portable devices all the way to large scale systems like energy storage devices. So I hope that from all these points that we gather, see the importance of electrochemical systems. And specifically, just as a side note, my lab here works on electrochemical flow systems. So these are batteries again, positive electrode, negative electrode. But instead of having the electrolyte inside the cell as an enclosed device, the electrolyte is stored in external reservoirs. And this is useful, this modular useful is important for many reasons, one of which is very apparent, is that by just playing with the size of the electrolytes, you can change the scale of the system based on the end user needs. So you can have high capacity basically by increasing the electrolyte volume and your tank size, or reduce it. And so I'm using these electrochemical flow systems for energy storage applications, for carbon capture applications, and for lithium extraction applications currently in my lab. Okay, so now that we know about electrochemical systems, why in situ or Operando characterization techniques are critical in the context of electrochemical systems. So I think that the most traditional way of analyzing the operation of a battery or an electrochemical cell is that I'm sure you've seen it, charge, discharge, cycles. We apply a voltage or current, measure the responding current or voltage. And that's how we decide what's the efficiency of the system, what's the life of the system, how stable is this battery, stuff like that, right? But that's a very simplistic view of what's going on inside a battery or an electrochemical cell. At the molecular level, the species that are in that device, they can undergo complexation, they can precipitate, they can degrade over time. So there are stuff happening at the molecular level that affects the degradation, affects the resistances in the system. This is an electrochemical reaction happening on the electrode. It's a heterogeneous system, right? So we have interfacial level phenomena happening, the wettability of the electrode, the double layers that are forming on the electrode surface, the dispersion, mass transfer of species through the pores of the electrode. They are all going to affect your resistances, your voltage in the system. And of course, component level, system level stuff that's happening in the system. For example, a membrane, the component itself can degrade over time, and mechanically or chemically degrade over time. So again, that affects your overpotential, that affects your voltage measurement. So the voltage or current we measure is a macroscopic result of multiple coupled and often hidden phenomena across different scales. It just tells us the combined result of all these phenomena that are happening in the system. So we need in situ and Operando techniques to reveal the hidden electrochemical processes that are happening in the system. So based on the scale and the level that we need to detect, we need to choose our characterization technique, microscopic, spectroscopic, or electrochemical technique. Just a side note, before going into talking about the case study, the electrochemical carbon capture, I wanted to talk a little bit about the terminology of in situ versus Operando. It was something that was very confusing to me. And this is what I found in literature about this terminology. The terms in situ and Operando seems to be originated from the heterogeneous catalysis, the differentiation between the words. And so in heterogeneous catalysis field, they use in situ terminology for when you study, for example, your catalyst, your electrode surface, its performance, but you're not necessarily detect or study the performance of the device that this catalyst is integrated into. So, for example, you're observing electrode surface changes during charging using microscopy, that's in situ study, without measuring the device performance. Whereas Operando in the catalyst field is one step more advanced. So you are looking at, for example, the surface change of the electrode while the system is operating, and you are measuring the device performance and detecting those numbers as well as the numbers related to your component of interest. So Operando is often considered a subset or advanced form of in situ analysis. But since then, this terminology has been used in other fields, and often it's a source of debate. I found contradictory publications on using this terminology, and sometimes interchangeably. So what I'm going to do is that in this talk, I'm going to use them interchangeably. And I define and show how the experiments were done so we can decide whether this was strictly in situ or Operando. But I think this note was important on the terminology. Okay, so from this point on, I want to, now that we know the importance of electrochemical systems and the importance of, in general, why in situ techniques are useful, I want to show results within the context of electrochemical carbon capture. These are based on two works that I started during my postdoctoral, but they continued, dragged until last year they were actually published. So to show both of the combination of characterization and electrochemical system. Okay, so first, overview of the system. What is an electrochemical carbon capture system? Okay, so CO2 captured can be electrified. And that means that instead of using pressure or instead of using high temperature for adsorption and desorption of carbon dioxide, we can use voltage gradients. And so that's attractive. Why? Because it means that hopefully you don't need to go to high temperatures and pressure. So you are in ambient conditions, easier. The electrochemical systems we work on are flow cells, again, scalable. I very briefly explained the modular design of electrochemical flow systems. And the system that we are working on is aqueous. So it's actually water-based system that's being pumped into the cell for the redox reaction to happen. So for these reasons, it's attractive to work on electrochemical aqueous electrochemical flow systems for carbon capture, but exactly how voltage, applying voltage can result in carbon dioxide capture, right? So the species that I work on both in redox flow batteries and in carbon capture is based on anthraquinones. So these anthraquinones, you see the three-ring aromatic compound here with two carbonic groups. These organic species, they are redox active. They can undergo electron transfer. So by applying the right voltage, we are able to reduce this compound to through a two-electron transfer reaction. And this reduced species is going to gain nucleophilicity, right, on the oxygen groups. Its electron density is going to increase. And as a result, it can form complex with carbon dioxide and form this species. So on the two oxygen groups, it can form a complex or adduct with CO2 and form this AQ or anthraquinone CO2 adduct. Now, the nice thing about this is that, so here we apply the voltage to reduce it, then a chemical reaction happened and formed this one. But this species, this adduct, from now on, I'm going to refer to it as an adduct. This adduct is also redox active. So if we apply the right voltage again, we are going to be able to reduce, oxidize it back to the original species and release the CO2. So basically capture through forming the complex and release into the concentrated stream for storage or for converting it to other fuels. You can apply the voltage again and convert it and release the CO2. So this is the direction, the route of the reaction, but also these anthraquinones turned out to be undergoing a type of reaction that's called proton-coupled electron transfer, which is basically what the name suggests. During the electron transfer, they have protons transferring, either consumed or produced, okay? And so it turns out for these anthraquinones, at different pKa's, but generally the same direction exists, that below around pH 13, 14, depends on the pKa of the compound, it's going to either undergo 2-electron, 1-proton transfer and 2-electron and 2-proton transfer. Okay, why that matters? So if we reduce the species and instead of complexing with CO2, it becomes protonated because proton has been transferred, right? Either 1 proton or 2 proton. It's gonna increase the pH of the solution because you grab protons, hydroxides are there, the pH is gonna go up. And so when pH goes up, CO2 dissolves and forms bicarbonate or carbonate in the system, right? So there are two possible routes for this capture and release to happen. Either the species reduced, we apply voltage, it complexes with CO2, nice, or it becomes protonated, and once it becomes protonated, pH goes up. It's called the pH swing carbon capture route, okay, because pH swings up. And again, this phenomena, this species that has formed is redox active, and you can apply the voltage and convert it back to this oxidized form. So either routes are going to give me a carbon capture. So we then move to actually designing a system around this. So my colleague, Dr. Jing, synthesized these 3 isomers of anthraquinone, and I built an electrochemical flow system based on these isomers and operated the system. And for sure, this is a CO2 sensor during the charge or reducing the anthraquinone, and during discharge or oxidizing the anthraquinone. And as you can see, the CO2 sensor is registering a capture and a release, and we quantified that and also quantified the energetic cost that's going into discharge and discharge. And obviously, based on how much current density you want, how fast you want this reaction to happen, you have a different energetic cost. So the energetic cost was respectable between 70 to 140 kilojoule per mole. Of course, it depends on whether you have oxygen in the system or not. But the general overview of this work was that the first quinone, aqueous quinone flow chemistry was introduced under ambient condition, ambient temperature and pressure, and it reached the theoretical capacity under the conditions that we had no oxygen. In presence of oxygen, the efficiency was half of what it could have been. Okay, so we did this, and then the question is that, okay, you showed that it works. What is missing? So I wanted to be able to improve this system. It had efficiency losses. It had, as you can see, under some conditions, it didn't capture the whole thing. Even under nitrogen, there were differences in the energetic cost depending on how we operated it. And so I needed to know what's happening in the system to be able to then decide how I can improve it, right? The problem was that, as I just showed, the electrochemical flow system that we operated and traditionally people use for showing, carbon capture and release has happened is that in the downstream, we have CO2 sensor flow meters, just like the CO2 sensor data that I showed, that registers how much carbon dioxide was captured and released, right? It doesn't know where is the source of that capture and release, what phenomena contributed to that capture and release. It just shows you that this much capture happened and this much release has happened, right? So for me to be able to then know the contributions of these 2 pathways that I just mentioned, I needed to be able to do in situ mechanistic analysis of the system. Now, you might ask, why did you need to know exactly quantify the reaction pathways contributions to be able to improve that, to engineer that? You know how much was captured and released, just work with that to design better systems. Well, there are many important reasons, important information that we will be able to gather by knowing what's happening inside our system. So for example, capture capacity. If it happens through this route, it's gonna be 2 CO2 captured per 1 mole of anthraquinone. If it happens through this route, based on the first reaction, it's gonna be again 2 to 1, but the second reaction is gonna be 1 to 1. So capture capacity can be half of what is possible depending on what reaction pathways it goes. Energy requirement. The voltage that I apply to recover this species versus this species is very different. This is the voltage signal pertaining to the anthraquinone that hasn't complexed with CO2, the oxidation peak, versus the one that has complex. You see that it's completely shifted, different energetic cost. System stability. Am I dealing with this compound degrading over time or this compound degrading over time? Reaction kinetics are different in these 2 reactions. Material selection. I need to be able to design a membrane for my system, right? If I form bicarbonate and carbonate, they can cross over to the other side of the battery, depending on what anion exchange membrane we are using. So I need to know to what extent, under what condition this other route is happening, and also scalability, which depends on the solubility of this. So in situ study, mechanistic study, understanding these contributions is not a fundamental study. It goes hand in hand, fundamental engineering of the system. You need to know one to be able to do the other one and improve the other one. Okay, so before going into the in situ characterizations, I think we need to have some prediction, some expectation of what's going to happen in our system. Do we have a view of the equilibrium and kinetic of our system? It's important to have that perspective before designing your system for in situ study. And so I'm not going to go through a whole thermodynamic analysis, but just an easy overview. We said our compound can capture CO2, that's one equilibrium. Our compound can be protonated, that's another equilibrium. It can be protonated with 1 proton or 2 protons. Remember the Pourbaix diagram I showed? Again, those each have their own equilibrium. If protonation happens, CO2 will form bicarbonate and carbonate. That's another equilibrium dynamic that's happening in the system. We need to maintain electron neutrality at all times in the system. AQ ultraquinone is dissolved at a certain concentration, no matter what it has been converted to, it's conserved. So we have a conservation limitation there, and water equilibrium, and we have the Henry's law. The CO2 that's dissolved is dictated by the partial pressure of CO2 at the overhead. Okay, so doing this analysis gave me a view, a prediction of what thermodynamically at least is going to happen in my system. So the plot on the top left is showing that based on the adduct, the AQ-CO2 complex equilibrium constant, we can have a very different system. So if you choose an AQ in the range of 10 to 4 to 10 to 10 equilibrium constant, you're going to mainly get bicarbonate-carbonate. Very strong tendency for complexation, of course, is going to dominantly give you AQ-CO2. But then there are regions where you have the combination of both phenomena happening in your system. And of course, all of this that I showed here depends on what pKa your AQ ultraquinone has, under what partial pressure you're operating. Shifting it to very low partial pressures like direct air capture, it's going to shift it to CO2, so carbonate formation. You are going to have 1-to-1 capture capacity, and we could predict the concentration speciation between the species. Okay, so depending on what AQ I choose, I can have one of the two extremes or the combination. That at least that's what thermodynamic tells me. However, something can be thermodynamically favorable, but kinetically very slow to happen, right? So I needed to know some idea about the kinetics of the system, right? So here what I'm showing is a current voltage cyclic voltammetry. It's current voltage plot. So we sweep through the voltage and read what's the current out of the system. And what it does is that I can play with the rate of sweeping voltage. That would affect how fast I'm producing that reduced form. And that reduced form is undergoing, one of the reactions is a chemical reaction complexing with CO2, right? So I can play with the rate of the reactant forming, and as a result, play with the rate of the chemical reaction formation, right? And so the signal for the voltage of the adduct, as you can see, is changing because I am changing the rate of the voltage application to the system, right? So why I did that? Because we could then once we have data of how the reaction is happening with different concentration formations and the rate of the voltage, we could feed it to a model and predict the kinetic rate of our chemical reaction. So the plot on the bottom right is showing the fit between the experiment and simulation, which gave us some kinetic numbers for the ultraquinones that we are studying. So just to give you the final conclusion, the thermodynamic view predicted that for the specific isomers, the BT map AQ that I showed earlier, actually it's strongly going to bind with CO2. So thermodynamically, it's predicted that your adduct formation is going to be dominant, it's going to win. Whereas the kinetic view gave me numbers, the kinetic rate of formation of that adduct was slower, in some cases an order of magnitude slower than the rate of bicarbonate and carbonate formation. So this specific species that we made a device out of, thermodynamically at equilibrium, it's going to equilibrate to all formation of adduct, but kinetically, it predicts that actually you're going to form bicarbonate and carbonate in your system. Be careful about that, right? So I really needed to know, because there is a contradiction here. It's not a contradiction, but equilibrium and kinetic are going to be different. It means that there is going to be a dynamic interplay between these two pathways, and I needed to know that dynamic. I needed to be able to quantify it exactly. And so from this point on, it wasn't about engineering the device. It was about finding methods that we can characterize the system in situ during operation. By characterization means quantifying this interplay between these two reactions. Okay, so I earlier showed that the redox potential of the AQ that's complexing with carbon dioxide is that it has a separate, distinct voltage signal, this one, compared to the AQ that's not complex with CO2. The reductions are overlap, but the oxidation is what I see a distinct signal, right? So I wanted to use that. So I'm saying, okay, at voltages where this signal, if I see this signal in my voltage profile, it must have been adduct forming. And if it's shifted to the negative value, it must have been my AQ form. But the problem is that in an electrochemical system, in a battery, you are always measuring the cell voltage of the system, right? Things are happening on your negative electrode, things are happening on your positive electrode, and you measure the difference between these two. You don't know exactly what is your positive electrode's contribution and negative electrode contribution to that cell voltage. It's a combined effect, right? But what we can do is that we can put a reference electrode inside in our setup. So a reference electrode is a high resistant path that wouldn't let current to pass through it. So it's going to maintain a stable potential, and it has a standard stable known potential. So if I put a reference electrode in my setup, and during operation, I also measure, you just literally connect your potential stat channel voltmeter between your positive electrode and your reference electrode, as well as negative electrode and the reference electrode. You could exactly see what's happening there, what's happening on the other electrode. The combination is your cell voltage. You can also check if your setup is correct by comparing this number with your cell voltage. And this is quite easy in flow cells because electrolyte is outside of the cell. I don't need to put the electrode inside the system, which is might interfere with your system. Okay, so that's exactly what I did. There is this reference electrode in the path of the electrolyte. This is the actual setup. And so the cell was operated, but it wasn't operated again. It was about testing whether this approach is sensitive for quantification. This is not how electrochemical carbon capture is operated. I operated it under 100% nitrogen, no CO2. It was charged, AQ was reduced. And then for a set amount of time, known amount of time, like an hour in this case, I purged carbon dioxide into the system at 10% CO2, 90% nitrogen. Give it time, 1 hour, for whatever reaction that wants to happen, and then switch to nitrogen and discharge the system. So this time would allow for some adduct to form. All can be adduct, some can be adduct, none of it can be adduct. I just gave time to it, right? And then the discharge voltage, remember, I have a reference electrode, so I can exactly see what's happening on the electrode where the carbon capture is happening, right? And indeed, I saw two plateaus. One is the reduced species. The potential is close to the potential signal signature that I showed earlier in an ex situ test on cyclic voltammetry, and one very shifted to positive values. That should be for adduct, right? So from the capacity that was delivered at the signal voltage signature of the adduct, so this one, I could tell how much adduct has formed, right? So I found the signal, I saw that it's delivering capacity at that signal for this amount of time, so I knew that I could calculate how much adduct, back calculate how much adduct has formed. And so the reason I designed this experiment this way is that I could play with the time, so 15 minutes all the way to 7 hours, to play with the kinetic and pushing it to equilibrate and see how the what is the adduct contribution, right? And remember, I have CO2 sensors at the downstream, so I can calculate what is the total amount that the CO2 sensor is telling me has been captured. I can calculate from the voltage signal how much of it was from the adduct formation phenomena. So the subtraction should be another route or multiple other routes. But for now, we know one other route that can happen, and that's pH swing, right? And so very interestingly, following our kinetic and thermodynamic analysis, we found that at a short amount of times, which is kinetically restricted, right? 15 minutes, half an hour, my sensor is detecting more than what my adduct is delivering, which means that pH swing has happened, which we know that because pH swing kinetically was faster. We expected it to be faster. And as I let it equilibrate, I let 7 hours under CO2, all of my signal and my CO2 sensor overlapped, and I was delivering the total amount through that adduct formation pathway. So the method was reliable. We did a bunch of other studies with this method, but there is a missing point here, right? I did the capture here in the yellow region. That's when CO2 capture happened, right? That's when I purged CO2. But I had to wait until I oxidized anthraquinone during the discharge to be able to tell what happened during that capture phase, because it's the voltage signal during discharge that allows me to do this quantification. So it's in situ, but wasn't really in real time, right? And also this process only worked when the species had really shifted potentials. If it was close, less than 200 millivolts, we saw that these signals are going to overlap in a way that is hard to quantify. Okay, so it was good for some cases, but still not real-time characterization. And so that brought me to finding other methods. And so the first thought I had was, let's look at the absorption. Maybe the anthraquinone that complex with CO2 has different absorption peak and from the anthraquinone that has not. And so I can calibrate and based on that quantify, right? So instead of putting reference electrode, the same setup, I put an in situ UBB spectrometer. And the plot on the top is under nitrogen. So I just first charge the system. The oxidized and reduced form, they have peak differences. So these two peaks are growing. This one is going down. There is a way to quantify, but I purged CO2 afterwards to force AQCO2 to happen. I'm showing here half an hour, but I waited a long time. I designed this experiment in different ways. It was very hard to differentiate any peak changes. There are peak changes, but it seemed that the absorption spectrum was overlapped, combined. It wasn't distinct in a way for me to use it for quantification in real time, right? So absorption didn't work. But then I thought, what if, okay, absorption is not distinct. What about emission? So maybe the emission plots have distinct signals. And so the plot on the left, these are ex situ, the two plots. I prepared the reduced, oxidized, and adduct species and conducted fluorescence study. And what I saw is that the adduct is very, very fluorescent and with high intensity. And actually, there are regions. So for example, if I look at this wavelength, this is excited at 405. If I look at this wavelength, there is a region that adduct is very fluorescent, but the reduced form is beginning to lose its fluorescence. That's good, right? That gives me some distinction. Excited at a different wavelength because our reduced form is a combination of reduced, protonated reduced. The peaks shift for the reduced species, but the important thing is that it's still distinct from the adduct peak. And so fluorescence, so with the right combination of excitation and emission wavelengths, for example, if we choose this wavelength, we should be able to follow adduct distinct from the reduced form or oxidized form. By the way, oxidized had almost zero fluorescence, a very low fluorescence emission, right? Okay, so this was promising, but in order to do in situ fluorescence study, we needed to build transparent cells because you can't look into a cell that's not transparent for fluorescence, right? And so this transparent electrochemical cell was designed by my colleague, Dr. Pochard, expert in microfluidic cells. A lot of expertise actually can be applied between these two fields. And so we built this transparent electrochemical cell, and a transparent electrochemical cell then can be put under fluorescence microscope. And but it needs all the other components, right? It needs to be connected to potentiostat. It needs to be connected to peristaltic pumps because it's an electrochemical flow system, right? So the reservoirs are outside. We need microfluidic gas pumps because we need to control the gas because we are doing carbon capture. And so through that setup, we could look, this is a fixed Z plane. This is the carbon electrode that was used inside this cell, just a wide field image to show that the system works. And so from this point on, now we focused on looking at the fluorescence of evolution of the fluorescence during operation. So we needed to set up two channels on this microscope, one based on the wavelength combination, excitation emission wavelength combination that allowed us to look at adducts from the ex situ studies, and one that was signature for the reduced species. So two parallel channels. And so the plots on the left are capacity, normalized intensity, the intensity that's normalized from the image that we are looking at. And also we have pH meter inside the solutions to just look at the pH swing because that's a signal that bicarbonate is happening. It can't be used, by the way. A lot of people ask me why they just didn't use a pH sensor, because as soon as bicarbonate forms, you will have a buffer in your system. And when you have buffer, there is no signal for you to quantify, right? Okay, so so at the beginning of the experiment, T0, we only have oxidized form, so no fluorescence, and we saw nothing. As soon as we started charging under nitrogen, so blue regions are showing in absence of CO2. The channel that was corresponding to only the reduced form, the channel 1, started fluorescing, and the other channel stayed silent, the adduct channel. And then we said, okay, let's purge 100% CO2. Let's just push this toward carbon capture. And indeed, we start getting a fluorescent signal going up in channel 2 and being lost in channel 1, showing the conversion in real time to adduct formation. And then once we started discharging, the fluorescent in channel 2 started going down. And we played with the current. And so this is capacity changing at different currents. And indeed, the fluorescent intensity was responding to that change in the current. And so just see it in a video. This is under nitrogen. Only the reduced form is fluorescing. Here is when we applied carbon dioxide, the other channel. You can even see the gas release during the discharge. Once it's discharged, it goes back to fully oxidized, no fluorescent. And so this is also something with a better setup can be used for studying the bubble formation because you can see the overview of the bubbles being released. That's the CO2 release during the operation. Okay, so the next step was to be able to use these intensities to be able to quantify. And at this stage, the setup that we had, there are no the downstream CO2 sensors. So there was not a combined number for me to subtract the adduct. It's a proof of concept. But we formed under conditions that we know adduct is dominantly forming. We operated the system to get the maximum intensity out of the image and correlate that with the concentration of the adduct that we know is forming inside that system. So a form of calibration so that we can do sort of quantification in the system. And then doing tests, for example, 100% followed by 100% nitrogen followed by 100% carbon dioxide in limited amount of time to restrict adduct formation to see whether the signal goes down or not, which indeed is corresponding to that decrease. Something that was exciting for me was looking at way more dilute carbon dioxide purging, whether I can see in real time adduct formation when I have only purged 1% CO2. And so this is the 100%, of course, was very clear. It's a high concentration, but even down to 1% CO2 with this AQ that we use, we could see in real time the intensity increasing, meaning that the AQ adduct was forming. This is something we can't detect with a traditional CO2 sensor downstream in the system. You have to wait for CO2 to accumulate for it to register with that sensor. And for 400 ppm, it was hard to see anything. It's not clear whether nothing formed or it's just so the resolution is so low that we can't see anything. And also we could do fast imaging to look at the kinetic formation. So I chose two of the isomers. The kinetic analysis that I showed earlier predicted that one of these isomers have lower kinetic rate than the other ones, with the exact numbers being 1 to 3rd. And so the interesting thing here is that when we did fast imaging, we could also get at least the slope of intensity change versus time was also 1 to 3rd ratio, corresponding to the kinetic analysis we did, which was with model feeding to experimental data in-depth analysis. So these all showed the promise. There are so much things that can be done now that we know that this method exists. We can use fluorescence microscopy, multiple channels for detecting the adduct formation versus the compound that has not complex with CO2. And so just to give you an overview, we talked about electrochemical systems, why they matter, and also why in situ techniques matter. And then we more thoroughly showed that in a specific example of electrochemical carbon capture systems, that knowing what's going on inside your system is going to help you design better systems. And we started by developing two characterization techniques, in situ reference electrode and in situ electrochemical fluorescence microscopy. And so moving forward, just I think 2 weeks ago, the bidding process finalized. And so we're going to have a new fluorescence microscope coming to our lab. It's capable of setting up multiple channels with different excitation and emission wavelengths with a powerful camera. And so it's going to be here in November or December. If anyone is interested in collaboration, work with this microscope, please let me know. And so this part is I guess it's about the events that are going to happen in October and January. Please join. Thank you so much.